Next, we're going to look at spontaneity and um, events that occur that lead to a lower energy tend to occur spontaneously, meaning, so I've got potential energy, it's high potential energy at the top of a hill, and water flowing down a hill is going to provide a lower amount of energy, and that's why water flows down and not up a waterfall. So we're going to take a look at enthalpy, entropy, and free energy to determine the spontaneity of a chemical reaction or process. Before we move on, I want you to stop and take a moment to answer this question. Once again, we are going to review this question when we get to lecture. So stop the video and come up with an answer. And as always, you can change your answer when we go over this in class. All right, so what is a spontaneous process? I mentioned it previously, but it is once the reaction or process has started, it proceeds on its own without any external influence or input of energy. Let's think of forest fires. Once somebody drops a little ember in the dry brush of a forest, the forest begins to burn, and it burns uncontrollably until you are able to put the fire out. You don't have to keep dropping embers, you don't have to keep striking a match in order for it to burn. Just like a candle. If you light a candle, you just strike a match and you give that candle just a little bit of energy to start burning the wax, right? It's going to continue until there's no more wax to burn. Now, a spontaneous reaction takes place only in the presence of continuous external influence or input of energy. So, let's say, what's a non spontaneous reaction um, that I can think of? Hmm, I have to think about that. I have to think about it and come back. Um, The reverse of a spontaneous reaction is always going to be a non-spontaneous process. All right. So if a reaction is spontaneous going in the forward direction, it's not going to be spontaneous going to reverse. Like, so if burning is a spontaneous reaction, burning the hydrocarbons in trees, right, is spontaneous going forward, we can't make the tree all over again once the tree is burnt down, right? It doesn't happen that way. But if we have a process that's not spontaneous going forward, it would rather go in reverse. And that would be a spontaneous reaction. We'll talk more about that when we get into equilibrium. So, thermodynamics can help us predict if a reaction will occur spontaneous, but we need a little bit more information. It's not enough because let's think about the process of melting. Melting is a spontaneous reaction. If the energy is, if let's say you have a piece of ice and it's at room temperature, it will spontaneously melt. Although it's an endothermic process. Well, why is that? Right? Like you have to put energy into um, melting ice, right? At room temperature, the reverse does not happen. It's not spontaneous. The reverse at room temperature, water does not freeze at room temperature spontaneously, right? Although it's an exothermic reaction. Hmm. So why is it that um, although we have an endothermic reaction, it occurs spontaneously? Because the idea is that most exothermic reactions are going to be spontaneous. And what we say is that exothermic reactions are what we call favorable, whereas endothermic reactions are unfavorable. Why? Because it's favorable to release energy versus having to put energy in. Remember, the universe doesn't want to have to do too much. The universe doesn't want to have to put too much energy out there, right? And if we're thinking of spontaneous reactions, let's think about it. Um, let's say your room is a mess and you go to clean your room. You have to put so much effort and time and energy into cleaning your room, folding your clothes, putting them in the drawer, sweeping the floor, mopping the floor, fixing your dresser, all of those things. But how easy is it for you to dirty your room? You come in, you kick your shoes off in the middle of the floor, you drop your clothes on the floor. That takes no effort at all, right? So it's going to be way more energy to clean up than it is to mess up, right? So spontaneous endothermic reactions, so just like we're talking about melting, why do they occur spontaneous if endothermic reactions are unfavorable? Where I have to put energy into something, if it's unfavorable, why does melting occur? Or why do some endothermic processes occur? Well, it's because there's an increase in molecular disorder when um, it's spontaneous. So let's think about melting again. You know that a liquid has more entropy than a solid. Why? Because those particles are able to move around and they're more disordered. So there's two things that are involved in spontaneity, whether a reaction is endothermic or exothermic, and whether there's either an increase or decrease in entropy. So we need two things to help us describe why a reaction is going to be spontaneous. So the second law of thermodynamics is that the universe spontaneously tends towards increasing disorder or randomness. So, and we know that entropy is a measure of randomness. So, a high entropy is a highly disordered system and it's considered favorable. Whereas low entropy systems are unfavorable. So if I actually increase entropy, so if I increase entropy, the change in entropy is positive. If I decrease entropy, the change in entropy is negative. Remember, the negative values tell us that entropy decreases. All right. So a system that's highly disordered is favorable. It has a positive delta S. If the entropy of a system is, if a system is well organized, it's unfavorable and we have lower entropy. So what is the entropy change? The entropy change is a measure of the amount of molecular disorder. And the change in disorder is the entropy of a reaction. And just like delta H, entropy of a reaction is, or delta S, is going to be the entropy of our products minus the entropy of our reaction. So if delta S is positive, that means that there's an increase in disorder, favorable. If our delta S is negative, there is a decrease in disorder and it's unfavorable. Why? Because the universe does not like to be ordered. And notice that our units are going to be calories per mole times K. Hey, wait, times K? What's K? What does K represent? Well, I know what the kilocalories per mole, what the calories per mole or the joules per mole means. That means the amount of energy per mole. But what is K? Ah, temperature. So entropy is temperature dependent? Oh, okay. Entropy is temperature dependent. We know that when we think about a physical process, right? At higher temperatures, particles are moving around more, they have more disorder. At lower temperatures, particles have less entropy because they're ordered, right? And this is the same for our chemical reactions, okay? So if we're looking at a chemical reaction, How do we know whether our reaction is going to tend towards a higher or lower entropy, right? Well, we know number one that gases are going to have higher entropy than liquids, which are going to have a higher entropy than solids. Solids have the least amount of energy, right? So if I'm looking at a chemical reaction and I have solids in our reactants versus gases and liquids in our products, then that means that we have an increase in entropy. The reverse is true if I have solids in my products versus liquids and gases in my reactants. What else helps us to understand how entropy has changed? Well, the number of moles. So if you have more particles, they can have more arrangements in space. If I have one orange, that one orange can only arrange itself in one way in space. If I have 10 oranges, I can line them up in a row. I can line them up in zigzags. I can have them in all sorts of different orientations. So we can look at the number of moles on the left versus the right side of a chemical equation to determine if entropy has changed or not. So the fewer moles, if I have fewer moles on my reactant side to more moles on our product side, then our entropy decreases going in the reverse direction, and entropy increases in going in the forward direction. Same as when I'm looking at a gas going to a liquid to a solid, my entropy is going to decrease, whereas it's going to increase going from a solid liquid to a gas. So let's do a little practice. Does entropy increase or decrease in these following processes? Smoke from a cigarette disperses throughout a room rather than remaining in a cloud over the smoker's head. Increase or decrease in entropy? Yep, it's an increase. Water is boiling, changing from a liquid to a vapor or a gas. Does entropy increase or decrease? Decrease. I'm sorry, increases. Let's take a look at this chemical reaction. I've got 3 moles of hydrogen gas plus 1 mole of nitrogen gas, giving me 2 moles of ammonia gas. Does the entropy increase or decrease? Well, I've got 3 moles of gas. No, that should be 4 moles of gas. I've got 4 moles of gas on my reactant side and 2 moles of gas on my product side. So that means that entropy decreased during this reaction. Let's take a look at individual substances. Which substance has the greatest entropy? Helium gas or sodium solid? The gas. What about liquid water versus gaseous water? Gaseous water. Okay? So, once again, what are the 2 factors that determine the spontaneity of a chemical or physical change? The release or the absorption of heat, which is our delta H. And remember, the release of heat favors spontaneity, or an increase and decrease in entropy. And an increase in molecular disorder favors spontaneity. So what does that mean? That delta H negative is favorable and delta S positive is favorable. Okay? So, how do we know which reactions are going to be spontaneous or not? Well, if I have 2 favorable situations, I've got a negative delta S and a negative delta H and a positive delta S. Both of those are favorable, so the reaction is always going to be spontaneous. Always, always, always. Delta H negative, delta S positive, always spontaneous. So if you're given the value of delta H and you're given the value of delta S and the delta H is negative and the delta S is positive, it's always going to be a spontaneous reaction. the opposite is always true. So if I now have a positive delta H, which is endothermic, it's not favorable, and I have a negative delta S, which is a decrease in entropy, it will never be spontaneous. You will always have to continually add in energy. Now remember, every reaction, you must input that activation energy. So there's always a required amount of energy for a reaction to start. Remember when we looked at the graphs of our exothermic and endothermic reactions, they both had amount of activation energy, right? It's just that our activation energy for endothermic reactions is much higher than that for exothermic reactions. So if you want to know whether another type of process is spontaneous or not, you have to look at the relative sizes of delta H, or the magnitude of delta H and delta S. How do they compare to each other? So the free energy change, or delta G, is what we can determine, what we can use to determine spontaneity. So actually, delta G tells us whether a reaction is spontaneous or not. So delta G tells us whether a reaction is spontaneous or not. Delta G tells us if a reaction is spontaneous or not. And what is the equation? For any system, if you are given a delta H and you're given the delta S, you can use this calculation, you can use this equation to determine whether the process can be spontaneous. All right? So delta G, if it's negative, we call that exergonic. And this is a spontaneous reaction that is going to release free energy to do work, right? So free energy is a delta G. The free energy change is delta G, and it's going to be exergonic if delta G is negative. So what do we have to memorize? Negative delta G is exergonic and it's spontaneous. Positive delta G is endergonic, and non-spontaneous. Okay, just like we know that positive delta H is endothermic and negative delta H is exothermic. Okay, right? So negative delta G means that it's a spontaneous reaction. A positive delta G means that it's a non-spontaneous reaction, and it's going to absorb free energy in order for the reaction to occur. So let's take a look at, let me put myself here in the middle. What do these graphs look like? Hey, wait, it looks just like our potential energy diagrams. The only difference is the name. Oops, sorry, folks. The only difference is the name of the energy. Here we have Gibbs free energy, whereas in our potential energy diagrams, it was potential energy, or delta H. Here we still have our same reaction progress. And the difference between delta G from our reactants to products is going to be either positive or negative. And if we have an exergonic reaction, that means that our reactants have more free energy than our products, right? Products is delta G is going to be the same as delta H, products minus reactants. So delta G is equal to the free energy of our products minus the free energy of our reactants, okay? For an endergonic reaction, it's not spontaneous, and it's going to be a positive delta G, where our reactants have lower free energy than our products, okay? So spontaneity also depends on the temperature. At low temperatures, that T delta S, because remember that delta G is equal to delta H minus the temperature times delta S. Now, if you remember, delta S was, so heat is in calories per mole, whereas delta S is calories, well, that's kilocalories per mole. It's calories per mole kelvins. So whenever you're looking at delta G, you have to always convert either the delta S or the delta H to the same energy unit. So because delta H is always going to be kilo, whereas delta S is not. So it's either going to be kilojoules for delta H or joules for delta S. Kilocalories for delta H and calories for delta S. Okay? So at low temperatures, T delta S can sometimes be really small, making the delta H the dominant factor, right? So some reactions that are spontaneous at low temperatures will not be spontaneous at high temperatures. At high temperatures, this T delta S can be larger. It can become larger than delta H, and this is how we end up having endothermic processes that are non-spontaneous at low temperatures become spontaneous at high temperatures, right? Thinking about melting, right? Melting is not spontaneous at low temperatures. However, if I raise the temperature, melting becomes spontaneous. Why is it not spontaneous at low temperatures? Remember, because I have to put so much energy into it. It's endothermic, right? So endothermic processes that are not spontaneous at low temperature can be spontaneous at high temperature. And this is what we have here. So if delta H is negative, right, I have a decrease in, this is an endothermic reaction versus where I have low disorder. When I get here, I have a positive delta S, because minus T times a minus S gives me positive T delta S. So it depends on the delta G. The spontaneity is going to depend on whether I'm at high or low temperatures. Do not memorize this table. I'm going to say it again. Do not memorize this table. Use the equation to help you solve these problems. You can, if you're trying to determine if something is spontaneous at a high or low temperature, let's say a low temperature is going to be something like 0 degrees Celsius. Or no, I'll say, let's say 0 degrees Celsius. Remember, and we're talking about, so this is 273 kelvins. A high temperature, you could just throw in 100 degrees Celsius or 373 kelvins into that delta G equals delta H minus T delta S equation if you want to determine if a reaction is spontaneous at low or high temperature. Okay? So that covers the first part of Unit 8, looking at energy and reactions.